Good evening, ladies and gentlemen. The Institute for Mathematical Sciences, or IMS in short, is a university-level research institute at NUS. Its mission is to promote interest and research in the mathematical sciences and their applications. It brings together foreign and local mathematicians and scientists of diverse backgrounds for interaction, cross-fertilization of ideas, and collaboration in research. It also organizes public lectures to inform the general public of new discoveries and interesting ideas in mathematics, and lectures to schools to enthuse students in their study of mathematics. This evening's public lecture is organized by the Institute in conjunction with the Singapore Mathematical Society and the NUS Department of Mathematics and of Statistics and Applied Probability. The speaker is Professor Persi Diaconis of Stanford University, a legendary figure in mathematics. Professor Diaconis studied violin as a child at the Juilliard School, which is one of the leading music schools in the world. And then magic as a youth from Diaconis, who has been called the greatest magician in the US. From the age of 14 to 24, he pursued a successful and colorful career as a magician until his destiny was changed after a friend recommended him a book on probability which he could not understand. It led to his enrollment in mathematics programs in the City College of New York and Harvard University. What followed, as I say, is history. He is currently the Mary Sansary Professor of Statistics and Professor of Mathematics at Stanford University. Honored for his fundamental work in statistics and probability, including the mathematics of card shuffling. He was elected to the American Academy of Arts and Sciences in 1989 and the National Academy of Sciences USA in 1995. He was president of the Institute of Mathematical Statistics, a Gibbs Lecturer of the American Mathematical Society, and a plenary speaker at the International Congress of Mathematicians. Professor Diaconis is a man of many talents. If he had not met Diaconis, we would today be listening to his violin performance as we would do to that of such virtuosos as Jacques Persi. And if he had not been recommended a book on probability, we would today be watching his magic shows instead of those of David Copperfield. But fortunately for mathematics and for us, it was by a twist of fate that he became a mathematician. Was that a random event? This evening, Professor Diaconis will tell us more about randomness. It is now my great pleasure to invite him to deliver his lecture on the search for randomness.
Hello. Thanks for coming. What I'm going to talk to you about today is as close to I can say in public about the foundations of my subject. What does it mean to say something is random? And to help me remember, I've got little... So the search for randomness. And just so that you know what's coming in this talk, I'm going to talk to you about flipping a coin, And then I'm going to abstract a little bit and talk about a way that what we've talked about pertains to other random phenomena. I'm going to say a little bit of philosophy, not too much, don't get nervous. And then I'm going to talk about shuffling cards. Now, just to start at the beginning, so I'm a professional random guy, and for me, as close to a random phenomena as I know is that. You know, when you flip a coin and just whether it comes up heads or tails, that seems like my, primordial image of a random phenomena. And if we think about it for a second, actually, coin tossing is physics. That is to say, if you knew, when the coin leaves my hand, if you knew how fast it was going and how many times a second it was turning over, Newton tells us when it's going to come down, and if we know what its rate of spin is, we know how many times it's turned. And if you think about it, and I'll maybe refine this simple model in a second, but the parameters of flipping a coin, there's a point for velocity and a point for rate of spin. And I'll come back to this picture in a second, but I had my physics department build me a very careful coin tosser. And here's what it looks like. And I actually used to bring this to talks with me, but trying to explain to the airline authorities what is that gadget when you want to get it on the plane. What you can see is that there's a holder, and I'll show you a close-up of that right now. That's this holder, and a coin goes there on the holder, and you twist the knob. When you twist the knob, that thing goes down, and there's a spring there, and the spring goes ping, and the coin goes up. And we shot it often enough so that I got a picture of the coin going up. There it is up there. It goes up like that, and then it lands in the cup. Okay, so that, you should imagine. And the thing is, it always comes up the same way that it started. And it's the damnedest thing you ever saw. That is, 50 out of 50, ping, heads, ping, heads. And it's just shocking, viscerally, because it looks like what I'm doing like that, except it always comes up the same. Okay, so coin tossing is physics, and in fact, carnival pitchmen, and actually yours truly, can flip a coin with enough precision to make it come up the way we can. It's not quite as delicate a thing as you might think. So let me go back to that first picture for a second and talk about it, and then I'll show you a more refined version of it. So let's look at this. So a flip of a coin is how fast it's going, say velocity, feet per second, and omega is how many times a second it's spinning. And so a flip of a coin is a dot on this picture. Now let's think about that picture for a second. Look at points out here. That's coins which go up with very high velocity, but they don't have very much spin, so they're like a pizza, okay? And they don't turn over at all. Points up here are coins which are really turning like a bandit, but they don't have very much velocity, so they'll never make it. And there's a curve, which I've tried to indicate there by hand, where initial conditions below this curve have the feature that the coin never turns over. And then there's a second curve above that, and these are very easy curves to write down with freshman physics, where the coin turns over exactly once. And so let me show you the picture more carefully. This is what it looks like on a grander scale. And one thing to notice about this picture is that when you get away from zero, when you flip the coin vigorously, the regions get closer and closer together. So that means that tiny changes in initial conditions make for the difference between heads and tails. And of course, that's primordially why coin tossing is random. and we'll try to refine that in a second. If you wanted to read more about this picture, there's a very nice expository article by Joe Keller called The Probability of Heads, and he'll tell you where that picture came from, but you could derive it yourself as well. So if we flip a coin very vigorously, we're out there, and maybe the difference between heads and tails is pretty small. Question, when we really flip a coin, the way I'm doing it now, the way you do it when you flip a coin, where are we on that picture? Because that matters. Okay. So that's an interesting question, and I like to talk about it because somebody may have a good idea. So when I do that, is the coin turning over 10 times, 20 times, 38 times, approximately? Not so easy to know, actually. You know, I've watched a lot. And so the first thing I did is I went to the physics department and I got a tunable stroboscope. Blip, 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 blip. And I painted half the coin black and half the coin a neon, bright neon color. And then I did this, and a friend took the tunable stroboscope and waited until the coin froze. Okay, so then that would say how fast it was turning over in one sense. And the first thing is that, well, it took 7 hours, right, to do the experiment, and the coin never froze. You know, he never got it exactly right, but approximately right, and I'll tell you what the numbers are in a second. I then had the first good idea I've had, which is I took a very thin ribbon, a piece of dental floss, but plastic, very, very thin dental floss, okay, about 3 feet long, and I did that. We timed it, and then I unwrapped the dental floss, so I knew how many times the coin had turned over. Okay, so it's actually pretty easy to figure out how fast the coin is going. You just have a friend, you know, 1, 2, 3, flip, and he times it with a stopwatch. It's still, there's measurement error of all kinds. I'll tell you what the answers are, and then we'll come back to this picture. Experimentally, a 1-foot toss takes about half a second. And what that means is the coin is going up about 5.5 miles an hour. Not very fast. Using the tunable strobe, the coin is turning over somewhere between 35 and 40, at rate 35 to 40 revolutions per second. Now, it only turns over, it's only going for half a second. A typical 1-foot flip therefore makes somewhere between 15 and 20 revolutions. And actually it's even more compacted there. So it's not terribly random. It's actually pretty constrained. And as I said, this is checked by coin and ribbon and various other things. And I may come back and say more about that. So what does that tell us about the picture? Well, I'll tell you what it tells us about the picture. The picture looks great, but in the units of this picture, 5.5 miles an hour is, this is the velocity plane, a fifth. So if this 5, here's 1, a fifth is very, very close to 0. But it's 40 units up. Okay, so this picture tells you nothing about flipping real coins, in fact. But the math behind the picture tells you how tightly compacted the lines are up there, and they're very tightly compacted. And conclusion, there's a real sense in which coins, the way we normally flip them, are fair to 2 decimal places, but not to 3. What do I mean by that? From my experimental work, I know that there's a pepper of points up there when we flip a coin. It's not always the same. It has a little distribution. So there's a pepper of points, and you can ask what proportion of them lie above heads and what proportion of them lie above tails. And of course it's not 0.5000000. You know, it's 0.503 or 0.497. I mean, it's in that range. So coin tossing, there's a sense in which you can say coin tossing is fair to 2 decimal places, but not to 3. Now, in fact, and I'll get off this, but because I could talk to you about flipping a coin for quite a long time, real coins do something much more complicated than what I just said. If you take a real coin, and if you do this, and if you look when it lands, sometimes it's that way. It doesn't just turn over through an axis proportional to it. Real coins precess. They rotate about a funny angle. And when I was checking with my coin and ribbon, sometimes I found I do that, it looked the same, but the coin only turned over 3 times. They don't turn over the way you think. And I've actually recently done the math quite carefully with precession, and that number's still a pretty good number, and that is fair to 2 decimal places, but not to 3. But the most interesting thing we proved is that there's a constant bias. That is, no matter how vigorous, suppose you hit the coin exactly in the center, okay? Then it would go up without flipping at all, right? The best you could do was if you hit it on its edge, right? Exactly on its edge, and then maybe it would flip through the center. What we've shown is that anything in between, the coin is always biased to land the way that it started. No matter how vigorously you do it, the bias is built in. Let's work with Richard Montgomery, who's a 3-body problem expert, and you need somebody who knows about stuff like that. Okay, so that's some about coin tossing. I'm going to come back and say a little bit more, but I want to abstract for a second. Okay. Now, I wish I could do this really, but I probably shouldn't anyway. But suppose that wall here to the right was painted black and to the left was painted white. Okay? And suppose I had a real dart. Now, even I, as bad as I might be, I can make it come up black every time. Okay, that's no big deal. And now, and the image is as close to seeing the onset of randomness as I know, suppose I took the paint on the wall and rearranged the stripes into stripes, so that instead of being 6 feet black and 6 feet white, it was 1 foot by 1 foot in stripes. Well, still not so random. But if it's 1 inch by 1 inch, okay, as it gets closer and closer, it gets random. So let's talk about that for a second. And then I'll relate it to coins, and okay. So there's the dart on the wall, and this was one of the first ways that people try to come to terms with randomness, to quantify this. And it was Poincaré, a great mathematician of the last 19th century, really, died in the early 20th century, who studied this and made it quantitative. And here's one result that he proved. So suppose I say, I've got this dart, and it's going to land someplace over there, assuming it's going to hit the wall. And I'm going to take that wall and I'm going to make it from 0 to 1, just choose units that way. And the height, I've called it F, is the propensity, if you like, for the dart to come up at X, where X is a point on the wall. And so suppose there's some propensity. I'm just throwing the dart in my normal mode. I have some propensity. So let F be a probability density on 0, 1. What one wants to know is, if you rule the wall with width H, the observed proportion of, say, red will be the area above the red blotches on the line. And Poincaré showed that the probability of red, that's one of 2 colors, goes to a half as H goes to 0. Now, he showed much more than that is true, but let me say one sentence. Don't get nervous, this is the end of the math. But let's just say that you can make these things into math. Suppose that my function is continuous, doesn't have jumps. The chance of red differs from the chance of black. It's the area under the curve, above the red blotches, minus the area under the curve over the black blotches. Okay? Well, you can bring the absolute values inside and say that's the integral, that's bounded above by the integral between f and f shifted by h. Well, for continuous functions, that difference can be bounded by what's called the modulus of continuity of the function. It's how fast the function wiggles. And it's known for continuous functions that the modulus of continuity tends to 0. So that's the math behind that. Now, when you do it more carefully, you get this kind of thing. Here's the chance of red differs from a half by h how fat the region is, the integral of the derivative is a measure of how sharply peaked your throwing is. If you're very accurate, then your probability distribution would be very sharply peaked. It would have a very high derivative at some point. It might well. And that's a measure of how accurate, because after all, that has to come in. And for people who like doing calculus problems, that 8 is sharp. You can't improve it. Okay. This argument Poincaré called the method of arbitrary functions. Why? Because for an arbitrary probability distribution, in fact, quite general, our probability distribution, the chance, I don't care how careful you are, as those stripes get littler and littler, the chance goes to a half. And so that's a way of justifying probability. It was brilliantly developed by Eberhard Hopf, and I'm not going to be able to tell you much more about that. Now, the same type of analysis, first of all, is where I got my, let me find this nice picture here. Seems to have gone, but can't have gone very far. The same type of analysis applies here. That is, if I have an arbitrary probability distribution, and if I put it on top of this picture and I slide it away from 0, the chance will be a half, because half the area will be above black and half will be above white. Well, to give you an indication of why it's important to think carefully about that, I've given this talk several times, and I had a friend who taught high school, and he had a class of high school girls, and he asked them for homework to flip coins 300 times. Now, it's an awful thing to do to students. I mean, it takes 3 hours to flip a coin, 300 times, and it's just boring. Anyway, he came to me with the data, very excited, saying, how do you explain this? And the data was very patterned, head, tail, head, tail, head, tail. And it was patterned enough that I got interested, and I went and watched them. And the thing is, they were bored silly, and they would just do this, So you were down around here, and if you're heads, you go to tails, and tails, you go to heads. So where you are in that picture matters. Okay. Now, the same type of analysis that I just carried out can be said for many of the basic images that we have of physical devices. So I want to take you briefly through some of them. First of all, roulette. So probably people here all know how roulette is played. It's in standard casinos. There's a table and chips, and croupiers and lights and money. And there's a wheel and a ball. And then there's an inner wheel. So there's a round roulette wheel. And the ball is thrown around the outer wheel. There's an inner wheel which is spun and it goes the other way. Gravity eventually makes the ball go down and it rattles around and stops. That's roulette. Well, when I just began as an assistant professor, we started to think, a group of us, that roulette is a physical game. And they let you bet quite late in roulette. Is there a technical problem for you guys? No, I don't. I need you to calm down. Roulette is a physical game, and they let you bet quite late. And so we built a gadget which was like a little cigarette package. So we're standing there watching the roulette wheel. There's the ball going around. When the ball goes around a fixed point in the room, say that corner, you push a button. The button's actually on your arm under your jacket. Okay, you push a button. And then when the ball comes around again, you push a button again, and now the gadget knows how fast the ball is going. And then when 0 on the wheel comes around, you push a button. When 0 comes around again, you push a button. The gadget knows how fast the inner wheel is going. And then the gadget does a calculation, and it tells you where the ball will drop. Now, it's only accurate to within half a wheel. But if you're getting 35 to 1 on an 18 to 1 shot, that's like having a vacuum cleaner in the casino. Okay. So we actually built this gadget. I'm not just telling you this. We built it and we went and used it. And there are many interesting stories. I'll say one or two. One is we first did the math pretty carefully, but then I went and rented a real roulette wheel and we leveled it up and we brought it in and we measured it, and the equations didn't work at all. Okay, that's not so uncommon in the application of theory to practice. There's often a tuning phase. And what we realized after weeks of being stuck was that everything we'd done had neglected friction, as I did when I talked about my coin. Well, there are three kinds of friction that people talk about. There's sliding friction, rolling friction, and air friction. And the friction that really mattered was air friction. When they turned the air conditioners on, all the equations changed. The math wasn't useless. It gave us a simple parameterized family of curves, and we could put parameters into those curves, and then we went into the casino and we tuned our curves to match the data. That is, we tuned out one or two parameters so that they match the data pretty well. One of the problems is you've got to go actually make the money and bet, and you don't stand there clocking the wheel. So one guy stands and clocks the wheel and bets $1, and there's another guy with gold chains and etc. who makes the big bets. And the timing actually has to be pretty good. And one of the things we had to do was adjust by looking at the preliminary data, whether the guy who's tapping is a little early or a little late, and various things like that. If you wanted to read more about that, there's a very good book by Richard Bass. It's called The Eudaimonic Pi. Eudaimonis was one of Aristotle's good demons, and there's a group at Santa Cruz that had the same idea. And they went and built the gadgets, and the reason I know they built the gadgets is because if you read the book in the middle, I say there's three kinds of friction: sliding friction, rolling friction, air friction, and the friction that really mattered was air friction. I say, okay, they know what they're doing. They made the mistake of trying to use their feet to trip the switches, and your feet are very slow responders to the input of your eye, and they never got it to work, so they wrote a book. We did get it to work, so we didn't write a book. Okay. One of the problems, though, that you learn is that when you start hitting numbers with $25 chips in a casino, they get very nervous. And they don't know what you're doing, but they know something's wrong. And they just start, throwing the ball all kinds of crazy ways. Anyway, roulette is a physical game, and you can do something about it. Carnival wheels, you probably know what they are. They were what we started out trying, and it's not very fair to go to some guy and win a bunch of Kewpie dolls, but we did. I'd love to tell you about the mathematics of rolling dice, both fair dice and crooked dice. Joe Keller and I wrote an article in the American Math Monthly in 1989. But for example, we learned that some casinos in Puerto Rico, for example, at the time we were working, shave dice. So you have a die, but it's shaved off a little. And you want to know, can you go, we're not touching the dice, we're just thinking, right? Can you go take advantage of it? And that's an interesting story. Anyway, I shouldn't leave this list of examples without telling you this one. Suppose instead of my flipping a coin, I do this. I take the coin and I do that, okay? Is that fair? What are the chances of the coin coming up heads and tails? There's a right answer to that question. You don't know, because you don't know. Okay, that's the right answer. No, I have to think about it, I have to experiment. Let me at least try to explain. It's a completely different physical problem, and it has a lot to do with the exact center of gravity of where the coin is. And at least American coins, I haven't tried yours, have very pronounced biases. That is, 64D pennies, it's 80% tails. A given coin will have its own bias, but the bias is very pronounced. Now let me just show you some data. Took a class of kids, had them take a penny, and first they took the penny, this is 103 kids or so, they flipped the penny 100 times and they reported how many heads out of 100. And that's what came out. So this is just a histogram of 103 kids. And what you can see is it's centered at about 50, and it goes to plus or minus 10 or something like that. Okay. We had them take the same pennies and spin them on their edges. This is the spin data. There are some kids, these kids, the coin came out 8 heads out of 100. Coins are very, very biased, so you can try that out on your friends, and you have to figure out what's the bias of the coin. Now let me try to combine those two things just for a second. Be pretty hard to do the physics of a spinning coin, actually. Suppose I ask you this: if I take a coin and flip it, or if I take a coin and do that, is one fairer than another? Now, if I'd asked you that before you walked in here, out there, you'd say, what are you, nuts? What kind of a question is that? But it's not before you walked out there. When you let a coin, most people think that this is less fair than landing on the edge. But that's because of the psychology. They think if a coin lands in the hand, there's a hand there. Okay, let's neglect that for a second and just think about the randomness issue. When the coin hits the floor, before it dies, it does some of that edge stuff. And so some of the bias comes in. And, you could do experiments and think about it. So there really is a sense in which a coin tossed on the floor is less fair. And you could measure it, I'm pretty sure. I haven't tried to do it. I want to point out to this audience that you've just been sitting in an auditorium for half an hour listening to a guy talking about flipping a coin. I'm going to change the subject. Okay. The next little snippet is this, a little philosophy. So I lied to you in a sense. Of course, you have to do that to speak in a communicating way. I told you I was going to explain about randomness, and in fact, I snuck randomness in the back door. So the question is, what is that F? If you would have listened carefully when I was talking about flipping that dart, I said something like, well, F is the propensity for the dart to come, but F is a probability distribution. You can't get probability out without putting probability in, I'm afraid. And so what is F? How do I understand F? Well, Poincaré, who's the guy who invented this line of argument, just didn't care about philosophy and didn't talk anything about it. He thought the argument had a visceral content, and that was enough. Hopf, who was a great mathematician and did many different things, was what I would call a frequentist. He argued in the following way. Imagine that I had my coin tossing picture, and I flip a coin and I put a dot down at what the velocity is and rate of spin. And I flip it again and I put a dot down and so forth. Those dots would get darker in some regions of the picture than others. There'd be no dots out here. There'd be lots of dots where it's centered. And so as time went on, as you got more and more flips, there would be this kind of histogram of where the dots were. And for Hopf, F was a continuous or smooth approximation to the long-term frequency of initial conditions. And he argued that for any initial conditions, for any F, the coin tossing was fair. A problem I see with that is, I think the argument makes sense for one flip. I think that if I flip a coin once, it makes sense to talk about whether it's random or not. And frequency is wonderful, but it's not the only problem that there is. There's a world of probability and foundational thinking, which is called Bayesian statistics, which has as its forefathers Bruno Di Finetti, Frank Ramsey, Jimmy Savage, for whom probability represents a person's odds for observables. And that makes some sense. That is, if you go out of the room and you say, well, I've got this guy in here and he's going to flip a coin, and what do you think is going to be heads or tails? If you pick somebody outside, they don't know me, right? And they think, well, I don't know, 50-50. You know more, right? You could, what you know does, prior knowledge and information of that sort does come into judging odds. The Bayesian theory, I think, and I'm certainly not alone in this, but it's not unanimous, using notions of coherence and exchangeability gives an elegant theory which for me captures what's useful about probability calculations and protects us from silliness, and I'll come back and talk about that. At any rate, let me tell you what I think F is, and here's my answer to what is F. F is my best guess, and what I mean by that is if I gave Warren Ewens here a water pistol and he pointed it at me, okay, and said, where do you think that next flip is going to wind up? I'd say, well, I don't know where it's going to. But actually, I know a lot about flipping coins, right? I have all this experience. I have all this theory I've done. And, he's pulling the trigger. And I said, well, wait a second. I think it's around here. And, it's more likely to be here. And it falls off that way. So F is my best guess, my subjective prior about the next flip, okay, the next omega velocity pair. And what the math shows is that F washes out if the flipping is vigorous, and if not, F matters, knowing, gee, the coin has just flipped a little bit. And this gives me a subjectivist version of objective chance devices. And it's quite a nice, it explains why different subjectivists are forced to agree about certain things and not about others. Okay, that's enough philosophy. Nobody can take too much of that. Here's another different kind of philosophical question. This one. Okay, so what? Does any of this stuff really matter? Flipping coins is one thing, okay? Actually, it can be important to some people. Before our Super Bowl, I often get calls from newspapers saying, well, you're the expert on flipping a coin. Is it really fair? And, okay, but what I mean by that is this thinking carefully about randomness, about the foundational nature of randomness matter. Well, I'm going to give you two answers to that, which you'll have to make do with, because I have one other thing I want to say. But here's my first answer, random numbers. And probably many of you know that every scientific enterprise, and many that are not scientific, make use of computer-generated random numbers. When you can push a button on your computer and it spits out what it calls random numbers. And how does it know? How does it do it? Well, often, unfortunately all too often, it uses a simple congruential generator of this form. It starts someplace, the number of milliseconds since the start of the day or something, which might be judged to be random. And then the next number is a fixed multiple of the last number, modulo some remainder. That used to be a popular one, 69069, I should say that Singapore has the great expert on random number generators, and to my embarrassment, he's in the audience, Harold Niederreiter, but I'm going to go on. So, unfortunately, many, and essentially every gadget that's used in a computer chip in a casino uses a simple generator of this type. They don't use any more sophisticated random number generators. And well, if you look at it, that's not random, that's completely deterministic. I'll come back, say a second. So here's a little look at what they produce. This is the random number generator that's in Microsoft and in BASIC and in the IBM PC. Here's what was done. You ask the random number generator, generate a whole bunch of points for me. These are points between 0 and 1, and make a plot of the first, where the coordinates are the first one and the second one. So take them in pairs. The first, second, that's one dot on the picture. The second and third, a second dot on the picture. Certainly what you can see, if they were random, they'd be scattered all over like raindrops. And what you can see from this is they're not random at all, right? They're striped and very far from random. Okay, this was the Turbo Pascal bit generator a little while ago, and what was done is it generates binary digits, and they were just plotted across the picture that way. And again, these are not random points. Let me bring it home in another way. I have done consulting for casino companies. Casinos are going completely away from physical random numbers, hand shuffle cards, or roulette wheels. Everything is an electronic gadget. Those electronic gadgets work this way. Okay? People like you are going in and watching the gadgets and figuring out what the random number generator is, what's the modulus, what's the seed, where is it, and then they know everything. And they're making a fortune, actually. Okay, that is, these are not secure, and there's still a while to go. So if you have nothing else to do, you might want to think about that. Let me go back. Where am I? George Marsaglia, who's sort of the dean of random number generators, about 20 years ago now, made a list of 10 tests, and between them, every random number generator in active use failed. Okay. This is an example just so that you know what I'm talking about. This was his birthday spacings test. So the birthday spacing test, you ask your random number generator to generate 500 random numbers. These are integers between 1 and a million. You order them, the biggest one, the next biggest one, the third biggest one, the 500th biggest one, okay? Look at the spacings, the gap between the biggest and the second biggest and the third biggest, etc., the spacings. Ask the question, how many repeated values are there among the spacings? Well, if I didn't know, I happen to be the one who did the theory for this problem. George asked me and I proved the theorem. But if I didn't know how to do the theory, the first thing I would do nowadays is go to a random number generator and ask it. You know, do this a million times and ask it what the answer is before I try to prove anything. Well, Don Knuth, who's the world's greatest computer scientist, had a random number generator that he said, if the honor of the country depended on it, this is the generator I'd use. The birthday spacing, it died completely on the birthday spacing test. It gave 16 times the wrong answer. I mean, there's supposed to be something. The theory is this number of repeated values should be approximated by a Poisson random variable with this parameter, and it's actually t cubed over 4m. And Knuth's test failed, this test. Knuth's generator failed this test, and every random number generator, including Marsaglia's, failed at least one test. Now, just for fun, and this is something that Harold and I can talk about tomorrow, every generator failed except this one. And I like to say this because maybe somebody will find a test that fails. Here's a generator. It's a second order recurrence. It requires you to take 55 numbers, put them in a memory register. That way, it's a 55th order recurrence. The next one is the product of the 124 back and the 155 back. And that's not arbitrary. The polynomial 1 plus x to the 24th plus x to the 55th is a primitive polynomial, has very nice properties. And this generator has very good properties theoretically, but also I've been using it for about 15 years. On every time I prove a theorem, I try to test it out on this, and it always seems to give the right answer. And then I give talks like this, and so people really have tried to crack this, find something wrong with it, and nobody has, at least not that I know so far. So that's the one I use. So that's one answer to, does it matter? Does thinking about randomness matter? It does. If you just think randomness comes out of a black box and it's perfect, well, somebody's going to win your money. Or your computer code can be off. Now, it's not horrible. It's a little like driving. If you think carefully about it, and if you use the best available random number generators, not the one that's naturally in your computer, you can drive carefully, you can, have safe sex, and you can use random numbers carefully, okay? But you do have to know what you're doing, okay? Here's my second example of does it matter? Okay, and this is actually the reason I got into giving this talk. So I'm a statistician, and statisticians nowadays do something, I guess it's a noun and a verb. Anyway, they do modeling. And they invent rather fanciful mathematical models with all kinds of made-up parameters. They assume things are linear and that variances don't change and that distributions are normal, things like that. And then they snow the rest of the world by saying, look, the model says this, and therefore we should use this as our public policy. And I'm not afraid of the math, and I'm not afraid of the models, and I'm not afraid of them. And that is important because it's like doctors testifying against each other. Somebody within the community shouldn't say anything bad about the community. Well, okay. Two two little examples. From mouse to man. How do we know how much carbon monoxide is how bad for you? It's an important question. I've spent years thinking about it, doing experiments. Can you extrapolate from animals to humans? Well, in fact, you can't. You can't extrapolate from mice to rats. Forget about extrapolating from mice to men. Yet, they have laboratory mice that are very delicately bred so that if you breathe on them, they fall over. And they puff a ton of smoke at them and they say, these are safe carcinogenic levels. You can say what you like, I'm not buying it. If you want to see the argument written out with arguments by both sides, it's not a one-sided street. Statistics is one of the few subjects that has discussion journals where I say what I think and the opposition says, oh no, you turkey. And so from mouse to man, it's a very nice article by David Friedman, and it's in a very friendly expository journal called Statistical Science. That article's in 1988, and it records that debate. But that's a case in which enormous decisions are being made on the basis of very, very flimsy mathematical assumptions. A second debate that I've been involved with is census adjustment. In the United States, we take a census every 10 years, and we use it to allocate funds to states. And it's known that in big cities, we undercount minorities and illegal aliens and things like that by a fair amount, maybe 5%. And what should we do about it? Well, there's a world of people quite willing to make up unverifiable mathematical models and use them, or at least try to get the government to use them in order to adjust for that. And again, this is not, there are people on both sides of the debate, but if you want to read a spirited debate, I recommend the article by David Friedman, which is called Census Adjustment in Statistical Science again. These models often have hundreds of parameters. The input, instead of being something you can measure from the world, comes as the output of other big mathematical models. Okay. They don't give as output anything that you can compare with the world. They give coefficients of whatever they mean. So the output is very, very hard to compare with reality. And I got extremely nervous about the directions my field was going in, and I wanted to know, is there some place where probability really works? Well, I went back to the basics, which was flipping a coin and throwing a diagonal, and you can see the difficulty I've had with those. You could just imagine the difficulty I have with these models. Okay. Now, nobody can take too much of negativity, so let me stop that and finish with the following. Here's shuffling cards. And there's a question, shuffling cards. How many times should a deck of cards be shuffled to mix it? I'll make that a little more careful in a second, but I mean by shuffle what you mean by shuffle. Well, what they mean in the U.S., you cut them about in half and you go the way you do. Okay, shuffle them together. How many times should you shuffle a deck of cards to mix it? So let me make math for a second out of shuffle and mix. I'm going to be working with a deck of n cards, and I'm going to be I want all permutations. There are n factorial permutations, and I want them to be all equally likely, at least to very good tolerance. And when people hear I'm studying shuffling, they say, well, can't you do that on computer? Well, actually, 52 factorial is about 10 to the 68th, and never once, if all microns, in the world were little computers, will they run through all arrangements of a deck of cards. You can't do it on computer. It's nice there are some things you can't do on a computer. Mostly you can do things on computer. Okay, by shuffle, for the moment, I'll make this more precise in a second. I mean, you have a probability distribution on the cards being in a certain rearrangement. I'll make that more precise in a second. So for each permutation, you assign it some mass, and the probability mass sums to 1. By shuffle twice, I mean, first you shuffle once, so you get some arrangement, sigma, and then if you want to get to pi after 2 shuffles, you had to have picked this thing. So this is the chance of being at pi after 2 shuffles, and similarly you could define the chance of being at pi after k shuffles. So this assumes that shuffling from time to time is independent, that it doesn't remember, and we can do more general cases, but this is enough. Finally, let me tell you about mixed up. This is what I'll mean by mixed. Don't get too frightened. The distance between shuffling after k times and perfect mixing is given by that recipe, and here's what that recipe means. Take some subset of permutations, say all permutations where the ace of spades is in the top half. You shuffle the cards k times, look at the probability that the deck is in that subset of permutations. Compare that to perfect shuffling, take the difference between those two numbers, and then take the question, the subset A, which makes that as big as possible. That's a distance, that's how well mixed you are. It's a reasonable notion of how well mixed you are. These ingredients specified, namely specifying a method of shuffling and a challenge number epsilon, we now have a well-posed math question. Given a probability distribution on permutations and an epsilon, how large should k be so that the distance to uniform is less than epsilon? And in case you're sleepy, thinking, is this lecture going to go on forever? The answer is no, and 7. It takes about 7 shuffles to mix things up. Does it matter? I'm not going to, well, maybe I will. Let me, because some people said, we hope you do a card trick. I don't do card tricks in public anymore, but let me tell you about one. Let's see, where's our Dean of Sciences? Where are you? Okay, so, hi, nice to see you again. Suppose that when I go home, I write you a letter saying, hi, thanks for all your courtesy and congratulations on all the good things that are happening at NUS. And I thought you might like to see a card trick. Notice I've enclosed a deck of cards with this letter. And there's a deck of cards with them. Now, you're here in Singapore and I'm back in California, okay? Take that deck out of the case, give it a cut, you cut it. Give it a shuffle, you're home, okay? Give it another cut, give it another shuffle, give it a few more cuts. The letter says, I'm sure you'll agree no living human could know the name of the top card. Now that sounds right if you're home, right? Take that card off, look at it, remember it, put it back in the middle of the deck, give the deck another cut, give it another shuffle, give it a few more cuts, mail me back the deck. Fast mail. Okay? And overnight, by email, whenever I get the letter, I say, you're thinking of the 7 of diamonds. And not only is it, but it's right. You're thinking of the 7 of diamonds. Okay. So I want to describe that trick for a second because that'll give you some information about the physics of shuffling cards. Of course, the deck I send you is arranged. And just for purposes of this conversation, suppose it's ace of spades, deuce of spades, 3 of spades, so forth in order. I might, in fact, actually mix the cards as well as I could and just write down their order on a sheet of paper because you might look. Okay. Now, when you shuffle cards once, why aren't they random? Well, you cut off some cards and you interweave them. These cards in the top half don't change their order. They're in the same order and same relative order, and the cards in the bottom half are in the same relative order. So the deck after one shuffle, before one shuffle it's all in one sequence. After one shuffle it's in 2 sequences, where you cut and this second sequence. Now I wish I could do this, but I can't. When you cut again, okay, this top half has 2 rising sequences. This bottom half will have 2 rising sequences. When you shuffle, there are 4 rising sequences in the deck. When you shuffle 3 times, there are 8 rising sequences. When you take a card and move it from place to place, that makes a 9th rising sequence. So what do I do when I get the deck back? I just play solitaire. I turn up the top card, say it's the 10 of spades, okay? If the next one were the jack of spades, I'd play it on the 10. Say it's not, 2 of diamonds, okay? I start a new pile. I keep going, there's the jack of spades. So I just play the card solitaire-wise, and that'll undo the 8 rising sequences. And when you do it, you'll find you have 8 piles, each about 1/8 of the deck, and 1 pile of size 1. Okay. Cuts don't foul anything up. They just cycle the deck and randomize it. So if that's true, and I probably wouldn't tell it to you if it wasn't, 3 shuffles is not enough to mix up 52 cards. And in fact, 5 shuffles is not enough to mix up 52 cards. 5 shuffles, the deck can have at most 32 rising sequences, and that misses a fair proportion of rising sequences, enough to foul it up. I call to your attention that I don't care how you shuffle. You can shuffle perfectly, you can do a terrible shuffle. After 5 shuffles, there are at most 32 rising sequences, no matter how you shuffle. There's no probability assumption there. In order to go further, I need a model, and I'll tell you just for a second the model we use. It's a model that was suggested by Ed Gilbert, Claude Shannon, and Jim Reeds. So I'm telling you what P is. And P is this. I said before, you cut the deck about in half and you go, how do I make math out of that? Okay, here's what you do. You cut the deck about in half, that is, you cut off J cards, and the chance that you cut off J cards is according to the discrete version of the bell-shaped curve, the binomial distribution. So you cut off J cards with probability 52, choose J. So, it's about 52. And now you start dropping the cards with your thumbs. And at any stage, if you have A cards here and B cards here, the chance that you drop the next card from here is proportional to packet size. So it's A over A plus B. I've just written that down. So that's a complete stochastic model for shuffling. Say you cut off 50-50. Maybe you drop the first card from here. Then there are 25 here, 26 here. So it's a little more likely that you drop your next card from here. And so forth, right? Just that you go sequentially. That's a very good model, it turns out, by experiment for the way real people shuffle real cards. It's not such a good model for the way I shuffle cards, but that's another story. Here's the way a theorem looks, and then this is about it. So this is for a deck of 52 cards, and I'm telling you the numbers. This is how far are you from random after K shuffles. After 1 shuffle, you're not very far from random. This total variation distance is the difference between 2 numbers, which are between 0 and 1. So it itself is between 0 and 1. It starts out at 1 when things are not mixed at all, and it goes down. But after 1 shuffle, it's not down at all. Now, that's not really 1. It's 99999 to about 20 terms. Okay? After 2 shuffles, it's 1 to 4 decimal places, actually to 15 decimal places. After 3 shuffles and after 4 shuffles, so the cards aren't mixed at all. At 5 shuffles, something starts to happen. 6 shuffles. At 7 shuffles, you can see it going down. And now it goes down by a factor of 2, and that continues forever. It keeps going down by a factor of 2 every time. Now, so how many times should you shuffle? Well, it actually depends how close you want to be to random. I can't answer that question for you. If the national security depends on it, you might want to shuffle 10 times. I don't know. But you know very carefully. Now, I'm a mathematician. Here's what it looks like as a theorem. This is work I did with Dave Beyer, who's an algebraic geometer from Columbia. So I've got a deck of N cards. That's how you know it's math. Instead of 52, it's N. And K is the number of times I'm shuffling. Okay, so if you told me N, how many cards are in the deck, and K, how many times you're shuffling, then that equation up there, K is 3/2 log to the base 2 of N, defines C as a function of K and N. You just solve that equation for C. The theorem says that the distance of shuffling K times to uniform is that horrible looking thing where phi is the normal distribution function. And without my trying to tell you what that formula is really about, here's a graph of the distance to uniform versus K, the number of shuffles. And what the math says is that you stay very, very flat until about 3/2 log to the base 2 of N. Then you cut down to 0, and you go to 0 exponentially fast, as in powers of 2. And this formula says, in fact, if you're a little less, you go to 1 doubly exponentially fast in C, and this goes exponentially fast in C. If you wanted to read about this, one place to read about, there are actually lots of places now, is in the paper I wrote with Dave Beyer, Trailing the Dovetail Shuffle to Its Lair, and that gives all of the details and lots about the card trick and etc. Okay, what I've talked about, this talk is called The Search for Randomness. Okay, I think you can tell by now that this has been my search for randomness, and I'm very happy you went along for the ride. Thank you. Sure, if there are any.
Before I invite questions from the floor, I'd like to make a short announcement.
Professor Persi Diaconis is going to give a talk tomorrow at the Institute's auditorium. And the title of his talk is Introduction to Random Matrices. It will be from 10:45 a.m. to 11:45 a.m. It's an odd time. Well, for those of you who have seen such an announcement before, the earlier talk by Charles Stein will be postponed. Professor Charles Stein is also from Stanford, and he's here. This will be postponed to next week, and that's why the time is odd. However, from 10:15 to 10:45 a.m., we have half an hour tea break. Supposed to be tea break, but we will continue with the little tea reception, not much. So keep in mind, if you're interested in random matrices, tomorrow 10:45 to 11:45 at Institute. Professor Diaconis will be speaking on that. All right, we have time for a small number. I don't know how small it's.
Questions or complaints? Complaints are also welcome.
Yes,
now it's your turn.
Okay.
Yes, sir.
I was wondering whether all random functions could be substituted by a series of sinusoidal functions, and which means frequency comes in. Thank you.
So I'm not sure if I understand the question. You were wondering if all random functions could be replaced by a handful of, or one sinusoidal function and a
Number of sinusoidal functions.
a number of sinusoidal functions. Well, it depends. It depends for what purpose you mean. It is in fact true that if you add up a bunch of cosines or sines, that the resulting sum does look like a random function in some aspects, but I think that I think that it would be very hard to use that in a practical way. I don't know that people have succeeded. I think I know what you mean, and I think that while we can say in some aspects, but pretty limited, a sum of a bunch of sine functions with incommensurate frequencies does look like a sum of, like a random number. It's only in some aspects, and in fact, if somebody knew that you were observing a sum of sines and they didn't know what signs you were observing or nor what the frequencies were, with a very limited data, they could go back and say, well, they have to be these frequencies, and you could then predict the future. So there's some limited sense in which it's true there is something that looks like randomness in a completely non-random phenomena, but just as people can crack random number generators by looking at the output, even very crude versions of the output, I think people could crack those kinds of random devices by looking at the output. So it a little bit depends what exactly you want to do with the randomness, I think, is the answer. Nobody wants to ask about bridge? Come on. Where? Yes, sir.
Do you agree with Benford's law?
Do I agree with Benford's law? So let me, thank you, that's a nice question for me. It's what I did my thesis in, and this isn't a setup. I never met that man before. Benford's law, for those of you who don't know, says that if you look on the front page of the Straits Times, for example, and you look at all the numbers on the front page of a newspaper, and you ask what, maybe there are 30 numbers, or I don't know, we're going to do this day in and day out. If you look at all the numbers on the front page of a newspaper, that you can ask how many begin with 1, how many begin with 2, how many begin with 9. And, well, if you haven't thought about it before, you might think, well, about a ninth. I don't know, numbers probably are random. They don't know about anything. And in fact, it's a fact of nature that in real databases, about 30% of numbers begin with 1. And that, when you first hear about it, what's that, about? And Benford actually not Benford, but earlier, Simon Newcomb, discovered that by looking at tables of logarithms, when people used to use tables of logarithms, and he discovered they were dirtier at the beginning than at the end. So people were looking up logarithms of numbers that began with 1, and then actually numbers that begin with 2 occur more than numbers that begin with 3. So there's a non-uniformity empirically. Now, there really is a non-uniformity empirically. Benford's law, about 30% is log to the base 10 of 2, and Benford's law says the proportion of numbers that begin with lead digit I is log to the base 10 of 2 of I plus 1 over I. And now it depends what kind of data you use. And Benford used tables of chemistry books. He would open up a book of, a handbook for engineers and look at all the numbers on the table. And sometimes it works pretty well and sometimes it doesn't. Just to give you an indication, suppose you looked at all integers, okay, and look at what proportion of them begin with 1. Well, of course, 1 begins with 1. But if you go up to 9, well, the rest of the numbers up to 9 don't begin with 1. So up to 9, it's a ninth. Okay. Now what about 10, 11, 12, up to 19? They all begin with 1. So when you go up to 20, it's about half that begin with 1. But now no numbers begin with 1 up to 99, and so it goes back down to a ninth. And then it goes back up to a half and back down to a ninth. And as you look at more and more numbers, the proportion of numbers that begin with 1 doesn't have a limit. And so there's not such a natural answer as about half of all numbers are even, because about half of all numbers are even, okay? So it depends on what kind of data you look at. So one of the things I proved in my thesis was that if you look, for example, at factorials, there's a table of factorials, about 30% of them begin with 1. That's a theorem. But if you look at powers of 10, well, powers of 10, they all begin with 1. So it depends on the numbers you look at. So you have to say a little bit carefully what you mean. And there have been lots and lots of explanations of Benford's law. I actually tested it by looking at the data and comparing it with the model, and the data doesn't fit the model as well as it would if the law were really exactly true, but it's a remarkably accurate prediction, and in fact it's used now to detect fraud. That is, when people want to know, do people make up the numbers on their income tax? Well, of course they do, okay? But if you want to test that, you can look at the proportion of times people begin with 1, and people who are making up the numbers make that about a ninth. They mix it up. And people who are using real numbers, it's about 30% that begin with 1. So there is a practical sense, and it doesn't, it's a pretty good approximation, and it seems to be useful. So I agree with it. I've studied it a lot. It's actually how I first came into contact with Harold Niederreiter, was his beautiful account of the fractional part of numbers mod 1. Thank you.
More question?
Yes, sir.
Yeah, I have a question about your random number generator.
Okay.
You mentioned just now that passed all the tests.
Mm-hmm.
Because I took a simulation class last quarter, and it seems like we're not supposed to add up.
I multiplied. It's star. Oh, go ahead. Okay.
Yeah, so you have a set of random numbers,
Right.
If this is like completely random, you can theoretically add up or minus off to get even more random numbers.
Or yes.
Yeah.
So if you make a more and more complicated function, then it ceases to become random. That's actually true. If you pick a function at random from 1 up to n to 1 up to n, it has periods of around root n, and it won't do for most applications. I'm not sure if that's the difficulty that you mean. This particular function is very carefully chosen. It's xn plus 1 is xn minus 24 times xn minus 55. Knuth's best generator used plus in between, and they're quite different, it turns out. And it has period around 2 to the 80th. It's a 55th order recurrence, and if I'm working mod 2 to the 32, it has a huge period. It has perfect spectral numbers in up to, I think, 55 dimensions or something close to that. But the main thing about it, it has very good theoretical properties, a reasonable theoretical property. The main thing about it is we've been trying to break it for years, just, empirically. Try out various things, and it just keeps passing all the tests. That's some practical advice I'm saying. It's not a theorem, what I just said. It's the result, though, of 20 years of people trying to break it. So It has good theoretical properties. It is used to some extent. It's not the hot new random number generator that's used. It's the one I would use if, and it wouldn't shock me at all if you guys sat thinking about it and said, well, here's a test, Mr. Wise Guy, and then it failed it. It's all it is what I said. I was just trying to give you, for my practical advice, that's the best one I know. That's all I'm saying. Really, it's shocking that something that is as widely used and as practically important as random number generator still has no really good theory. I mean, we've worked very hard. It's not that we have no theory, but the theory often applies only to complete circuits of the random number generator, not to parts of it, whereas all we use are parts of it. The computer science theorists have some theory, but they never deign to try it out in the real world. I'll just say they're theorists, right? I'm proud of it. But it seems to me to be a shocking state of affairs that something as practically important as that is not a mainstream activity of mathematicians and just has a few heroes like Niederreiter and George Marsaglia who keep us going, but they're important problems and there aren't good answers. So it's a great problem to work on. Now, I used to say in this talk that if you could make a chip which you can put in your computer and it gives good random number generators, you have a pretty good company. People are doing that now. I was asked to do it. Some of you may know the book Numerical Recipes, which is a great handbook of numerical analysis things. And the guys who put together Numerical Recipes put all the programs on a diskette, and that took up 10% of the diskette, and they wanted to put good random numbers on. And I'm Mr. Wise Guy, and they said, okay, Mr. Wise Guy, what do you say to do? Well, we used radioactive sources to get bits. Okay, we used a Geiger counter to blip and click. And one thing we found, that's supposed to be random. Physics says it's random. We looked and you could see the fluctuations of power. They're different in the morning and in the evening, and the rates were different. But we took many thousands of them, very long strings of bits. We XORed them all together. Then we did the data encryption standard to scramble them up. And that's what's at the back of Numerical Recipes now. I went back to basic physics to generate my random numbers. I tried to get them to use the best theoretical computer science generator, which is something like the Blum-Blum-Macaulay generator, and they just laughed at me and wouldn't do it, which I'm sorry about. But anyway, that's what I did.
Over there, one more question.
Yes, sir. Oh, yeah.
Can I ask you a question?
Yes.
What is your opinion? Is nature random?
Oh boy.
By nature random. You look at the elements of the different elements and the isotopic mass of individual element has a certain number. Alright? Let's say, for example, iron is 56 and
Sure.
55.
It's the periodic table.
That's right, the isotopic mass of the individual element.
Right.
So you have a series of relative abundance of the different elements. Now my question here is, have you done anything to this effect to determine whether nature itself is random, or is it just there is a certain law that it follows?
Well, people have, it's an open-ended question, and on one extreme, quantum mechanics, I don't have a line on that. And in fact, I was looking in Lewis's institute, there's still people are really debating whether it is randomness in nature. I just don't, that's above my head and beyond me and what I have to say. There are all kinds of regularities in nature, and the mind finds them. When the ancients looked up in the heavens, they saw bears and big dippers, right? The mind finds patterns in dots put down at random. And on the other hand, the planets are pretty close to being in the plane of the ecliptic, more or less, right? The planets are in a plane, and you could worry about whether that's random. And as far as I'm concerned, that's not random. There's a physical explanation for how gases flow and make things random. Similarly, people looked at so I'm answering your question not at the little level, but at a bigger level, but it's a very similar question. People looked at the distances between planets, at Bode's law, it was called, and you know, if you only have 10 numbers or 100 numbers, we get pretty good at making up simple formulas, and whether they fit a simple formula or not is a hard question, because people are trying many different simple formulas, and if you try many simple formulas and then find one that works, that's different than saying, before I look at the data, here's my formula, and now I'm going to look at the data, right? Those are two different things. So I think we can't really answer the question about something as simple as the structure in the periodic table. I don't think that's random at all. I think that you know, we have pretty good explanations for that. But whether nature itself has randomness, if you go down further and further, is an active debate. I think most physicists buy the standard interpretation of quantum mechanics, which has probability in it, and mostly they use the frequentist version of probability when they think about it at all. But great physicists like 't Hooft are arguing that no, they think it all can be explained on the basis of determinism. So who am I to have an opinion about that? And that's my answer. Yes, sir.
I was thinking whether you try using the white noise generator in the electrical circuit as a.
So the question is, have people tried using white noise generators? And certainly we have, and I'll tell you a curious story. You'd think it would be pretty easy to make random generators. You know, you use white noise, you know, a leaky capacitor, something going across, you could have a Geiger counter, you have a rotary switch and it goes 1,000,000 times a second. When the counter clicks, it stops. The problem is there's a mechanical interface on those things, and it's been very hard to get away from the problems with the mechanical interface. And the people who really think hard about fundamental issues of randomness, that's strange for me to say because I'm quite opposed to them, are the people who test for parapsychology. They make all kinds of white noise generators, and then we test them out, and it's very hard to do. They don't work when we test them. So somebody comes, a bunch of engineers, and said, this is it. Now we look, you know, we see, does it go even and odd half the time? Does it go up, down, up, down, up, down, the way it should? And they don't work. So what am I going to tell you? You know, I mean, it should be possible in principle. When we did our bits, we used white noise, and that's another thing that really showed fluctuations of when you took the data, what the rate was. And we try to clean it up, and there's a sense in which I used white noise to make my best random number generators, but I did an awful lot of post-processing, and I combined lots of noise together. So when we just looked at one stream of white noise, it didn't seem to work very well because of the mechanical interface. So in theory, absolutely, but in practice, you know, I think we still don't have good chips that I know about. And you know, the people are doing all kinds of strange things now. But I think when we look at them hard, they're not so random. That's sort of the point of my talk, which is, in theory, if you shuffle cards a lot, they're all mixed up. If you flip a coin very vigorously, it's close to 50-50. But in practice, we're lazy human beings. We all know that, right? And we probably don't brush our teeth enough either. Okay, so in practice, when you look at the way casinos and our computer programmers generate random numbers, they're flawed. And we have to not think of randomness as a black box and somebody else takes care of it. We have to think about, why do I accept this thing to be random? Based on what? And thinking that way, you can generate random phenomena, but without thinking, somebody can win your money. I'm going to stop. Thank you very much. Thank you.
If I have a word to describe Professor, no, that's yours. Persi, this is yours. This is yours. That was mine.
We've drunk together, Lewis. It's okay.
If I were to use one word to describe his lecture, I would say it's fascinating. Now, if I were to go to gamble, I have to start thinking of how the game is being played. And I would advise you to do the same. Thank you.